Every meter of space follows the same physics as every other meter. This sameness is not coincidence, it is a defining property of nature. You get the same numbers in a lab here as you would in a lab a billion light years away. That immediate repeatability is the payoff you can test experimentally. Picture a physicist on a distant world repeating your particle collision and getting your result. Space uniformity means equations do not gain secret location terms. You should care because reproducibility lets science be universal and portable across cultures and eras. The mechanism is translational symmetry, which treats space as uniform under shifts. In practice, shifting an experiment's position leaves its behavior unchanged after calibration. A concrete example is dropping a ball here and elsewhere, which shows consistent acceleration under gravity. Numerical experiments on Earth give about 9.8 meters per second squared locally. Short recap. Identical outcomes across place reveal nature's built-in spatial symmetry. A wide cosmic panorama unfolds, peppered with distant galaxies and nebular clouds. Saying laws look the same means the mathematical rules keep their form when we move around. This point matters because it guarantees physical predictions remain valid across locations in the universe. The central mechanism is translational symmetry, a mathematical statement that space is homogeneous. Practically, homogeneity removes location-specific terms from basic equations and simplifies modeling and prediction. Experimentalists test this by relocating precision apparatus and by comparing calibrated results across labs. For instance, atomic clocks in different countries agree to extraordinary precision after corrections for gravitational differences. These clock networks show agreement at parts in 10 to the minus 18 in many cases. An everyday example is how gravity accelerates a dropped object similarly across the same planet, ignoring local mass differences. So the picture emerges. Uniform space naturally produces invariant physical laws everywhere. Envision a globe that looks identical at every longitude. Symmetry in physics means you can change a system and still observe the same outcomes. Noether proved a remarkable link between continuous symmetries and conserved quantities in one elegant theorem. The mechanism works through mathematics. Invariance under a continuous transformation produces a conserved value by calculus and group theory. For example, if physical laws do not change in time, energy conservation follows as a mathematical necessity. Experimental confirmation appears in clock synchronization and energy accounting in closed systems. Atomic clocks across continents agree to high precision, while laboratory collision experiments conserve total energy within detection limits. As a concrete number, precision tests find energy conservation to many significant figures in particle experiments. Net result: symmetry is the deep engine that generates conservation laws we rely on daily. Picture two identical experiments run in far distant laboratories, producing matching data. By same laws, we mean the equations predicting outcomes remain unchanged across place and time. Scientists test reproducibility by careful cross-checks, calibration, and statistical analysis of independent measurements. The mechanism reduces errors and isolates systematic effects to reveal true invariance. A concrete example is the fine structure constant, which sets electromagnetic interaction strength. Laboratory spectroscopy and astronomical observations measure this constant and compare across billions of years. Current constraints limit variation to less than a few parts in 10 to the minus 6 over cosmological timescales. That numeric bound comes from comparing quasar absorption lines to terrestrial atomic spectra. So the takeaway is reproducibility across space and time gives us confidence in universal physical laws. Waves rolling across a calm ocean help picture this idea. Cosmologists call the universe's large-scale sameness homogeneity and its directional sameness isotropy. These properties matter because they form the backbone of cosmological models like the Big Bang framework. The mechanism most likely responsible is cosmic inflation, which stretched spacetime and smoothed variations. Observational evidence arrives from the cosmic microwave background, a relic globe permeating the sky, nearly uniform in temperature. Measurements show temperature fluctuations at roughly 1 part in 100,000 across the observable universe. That precise number provides powerful confirmation of large-scale uniformity and constrains models of the early universe. Bottom line, The cosmos exhibits remarkable smoothness, which helps physical laws appear consistent everywhere we look. Now consider that some laws might be emergent, not fundamental at first glance. Emergence means complex, large-scale behavior arises from simpler microscopic rules through collective effects. This possibility matters because universal-seeming laws could result from lower-level dynamics that average out microscopic complexity. The mechanism often involves symmetry breaking, where many microscopic states exist, but one macroscopic pattern dominates under given conditions. Superconductivity is a concrete example, where electrons pair and conduct without resistance below a critical temperature. Experiments show resistance drops below measurable thresholds at temperatures near a few Kelvin, consistently across samples. That numerical behavior illustrates how emergent phenomena create robust, universal outcomes. So the conclusion is emergence can produce apparent universality, even when microphysics differs. A close look at mathematics reveals why universal laws can be compactly expressed and strongly tested. Mathematics supplies the language and structures needed to encode symmetries and derive consequences. The mechanism uses group theory, tensors, and differential equations to enforce invariance in field equations and dynamics. For instance, Maxwell's equations maintain their form under changes between inertial frames, which constrains electromagnetic phenomena heavily. Numerically, these equations predict radio wave behavior from laboratory meters to interplanetary distances, matching experiments with many significant figures. That quantitative agreement shows math is essential, not decorative, in stating and testing universal physics. So the picture is clear. Mathematical symmetry organizes physical laws and enables precise predictions. How do we empirically check that laws do not vary with time or location? Scientists use diverse instruments and methods to probe the same constants and laws across scales. The mechanism is redundancy. Atomic clocks, particle accelerators, and astronomical spectroscopy crosscheck each other to reduce systematic bias. For example, atomic clock arrays detect temporal drifts at levels of parts in 10 to the minus 18 per year, which constrains short-term changes. Astronomical spectroscopy looks back billions of years, constraining variations of constants to about parts in 10 to the minus 6 across cosmic time. Particle accelerator experiments probe high energies, verifying local invariance under extreme conditions. These complementary approaches converge and produce tight numerical bounds on possible variation. Net result: a web of independent measurements supports the conclusion that fundamental laws remain unchanged over vast scales. We began with the bold claim that the same rules apply everywhere, and the evidence supports it robustly. Symmetries explain conserved quantities, emergence can produce robust universality, and diverse observations confirm consistency across space and time. The immediate payoff is real. Reproducibility makes physics a shared, global activity capable of predicting remote phenomena. When discrepancies appear, they point directly to new physics, and they trigger fresh experiments and theories. If this explanation piqued your curiosity, please explore our companion episode on symmetry breaking for a deeper dive. Thanks for watching, and I will see you next time.